Today, we're going to follow the secret life of a single pill. It's an absolutely incredible, unseen, and honestly often dangerous journey that starts the second you swallow it. So let's trace its path.
I mean, it seems simple, right? You take a pill, you feel better. But have you ever really stopped to think about the insane obstacle course your body sets up for that medicine? It's a pretty wild story of survival, chemistry, and biology, and it's all happening inside you.
You know, to really understand this, scientists look at it from two different angles. On one side, you've got pharmacodynamics, we'll call it PD, and that's all about what the drug does to your body. But for this explainer, we're focusing on the flip side, pharmacokinetics, or PK. And that's the story of what your body does to the drug. This is the journey itself, a four-stage gauntlet that scientists call ADME.
Okay, so every journey has a beginning. For our heroic little pill, the first massive challenge is just getting into the system in the first place. This is the A in our journey, absorption.
So what even is absorption? Well, in the simplest terms, it's the drug's big attempt to get into the party, and that party is your bloodstream. It's the whole process of moving from, say, your stomach into your circulation, where it can finally start traveling to where it actually needs to go.
Now, this first hurdle actually has three parts. First, the pill has to completely dissolve in your gut. Then, its molecules have to somehow get through your cell membranes. Think of it like trying to get past a really tough bouncer at a club. And only after all that can the drug finally enter the bloodstream. It is a tough barrier to cross, and believe me, a lot of potential drugs just don't make it past this stage.
All right, so let's say our drug made it. It's in the bloodstream, but the journey is far from over. Not even close. Now it has to navigate the entire body to find its target. This is the D in ADME. The distribution phase.
Distribution is basically the travel phase of this whole trip. The drug uses your bloodstream like a massive superhighway system, moving from general circulation out into the specific tissues and organs where it can actually do some good. But it's not as simple as just getting off at the right exit.
And here is where it gets really interesting. Not all of the drug that gets into your blood is actually available to do its job. A huge amount of it gets tied up, kind of captured by proteins floating around in your plasma. And as this quote points out, it's only the unbound, the free-floating drug that can actually leave the bloodstream and get to work.
Just think about this for a second. A massive portion of the drug, sometimes as much as 90%, can become bound to these proteins. Imagine the bound drug is stuck in a taxi. Yep, it's in the city, but it can't get out and actually do anything. It's only that tiny, unbound slice that's free to walk around and reach its destination.
So our drug has been absorbed and distributed. But at the exact same time, your body is already trying to get rid of it. This brings us to the final stages of the journey, the M and the E, metabolism and excretion. These two together make up elimination. The cleanup crew is already on the job. Your body has two main ways of cleaning house. First, there's metabolism. This is where your liver acts like a chemical processing plant, breaking the drug down into different, less active stuff. The second way is excretion, which is more like a garbage truck. It just transports the intact drug right out of the body, usually through your urine or bile.
This whole process of elimination is exactly why we have the concept of a drug's half-life. It's simply a measure of how fast the body gets rid of it. So if a drug has a really short half-life, its concentration drops by half super quickly, and that's why you might need to take another dose every 4-6 hours just to keep it working.
Okay, so we have all these competing forces, right? The drug is fighting to get in, travel around, and do its job, while the body is constantly trying to break it down and kick it out. So how on earth do scientists figure out the perfect dose?
Well, the answer lies in something called modeling. By studying this entire journey, the pharmacokinetics, and then combining it with what we know about the drug's effects, the pharmacodynamics, scientists can actually predict how a drug will behave in the body. The goal is to find that perfect sweet spot, a dose that works really well without being dangerous.
And that sweet spot has a name. It's called the therapeutic window. It's like a Goldilocks zone. If the dose is too low, nothing happens. It's ineffective. If it's too high, it can become toxic. The entire goal of drug development is to find that just right dose that stays inside this window for as long as we need it to.
And that really brings us to the core takeaway here. A drug can be unbelievably powerful in a lab dish, but that means absolutely nothing if it can't survive this journey through the body. As this quote says, a truly effective medicine needs a perfect balance. It has to be good at its job, sure, but it also has to be great at navigating the body's obstacle course. Absorption, distribution, metabolism, and excretion, or ADME. And that leaves us with a pretty fascinating final thought. We've talked about this journey in general terms, but everyone's body is a little bit different. So what if we could map out your specific drug processing profile? Understanding how your body and your body alone handles medicine could be the key to truly personalized treatments in the future. Now that's something to think about. Thanks for joining this explainer.